All right, good morning. Here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. So it is January 25th, 2017, and here we are for yet another lovely day for lecture number 4 in this lecture series. Now, today what we're going to talk about is we're going to discuss more of the subtleties of pressure and also some of the ways of measuring pressure. So we've already talked about how the difference between absolute and gauge pressure. So maybe I'll just review that a little bit here. What do we know about pressure so far? So let's review what we know about pressure so far from the previous lectures. Pressure review. Yes, there's going to be a difference between vertical and horizontal. Anywhere in the depth of a fluid, the pressure will be the same at the same elevation, but it will change at different elevations or different depths. So pressure constant at a depth, pressure linear, or pressure varies linearly with depth. Linearly although I will mention something very I will mention a subtlety of this. When I say a pressure varies linearly with depth, I'm of course making the assumption that it is an incompressible fluid. So for example, if you look at something like the atmosphere, the atmospheric pressure around you is not linear. It is it's an exponential type of thing, or a quadratic. I think it's probably exponential if I think about it. Simply because gases can be compressed. So if you the pressure doesn't linearly decrease as you go higher in, say, a hot air balloon or a plane. It's more complicated because air is highly compressible. So again, and this assumes two things. One, incompressible fluid. And so assumes, and two, at rest. So we're assuming the fluid that we're looking at is both incompressible but also at rest. And then also I want to mention gauge versus absolute pressure. Gauge versus absolute. Well, the difference here, of course, is that absolute is relative to atmospheric, and gauge is relative to the atmosphere. Oh, sorry. Wow, I really screwed that one up, didn't I? Sorry about that. Absolute is relative to vacuum. Helps if I did not have enough caffeine this morning, evidently. So absolute pressure is relative to vacuum, and gauge is relative to atmosphere. That makes me happy. That's a bit more proper. And somehow I started the slides on slide 4, but okay. I need to have more coffee in the morning. Great. Okay. So we've learned the difference between absolute and gauge pressure. We've learned how to calculate some applications of this. And you know what? Let's see. So I think we covered that pretty well. Now, one thing I would like to talk about, though, is how to actually measure atmospheric pressure, or how to actually measure pressure in a system. So, we know how to measure. We've discussed the difference between absolute and gauge pressure, but we've never actually talked about how you physically measure the atmospheric pressure around you, and this can be a bit difficult. So let's look at what kind of instruments we need to actually measure atmospheric pressure. The first and simplest way to measure pressure is to use a barometer. So let's discuss barometers, or a barometer, if you prefer. So let's look at a barometer. And consider this design of a barometer like this. So you're going to have an open pan of fluid, or an open container of fluid, and then a column of fluid, something like this. This is not to scale, and it would be supported through some means, but it's important that this column is open at the bottom. And then you're going to have a free fluid surface here and here. So there's a surface here, and this fluid is going to actually be all the way through the fluid and into the column. And there'll be a surface here, a free surface here as well. Now, let's look at what's in here. Well, I'm going to call this P1. And down here we'll have P2. And then if I look at and then what's pushing down this fluid will be the atmospheric pressure. So pushing down on this, I'll have atmospheric pressure. P atmospheric. Now the question is, what's causing this to rise higher? What's causing this fluid to rise, what's causing this column of fluid to rise above the fluid in the pan? And the reason is because the chamber above the fluid is evacuated. P1 is approximately 0. Basically it's a vacuum. Although you can't have a pure vacuum, what you will really have is the fluid's vapor pressure. If you remember from chemistry class, vapor pressure is the pressure a fluid creates when exposed to a vacuum. Or I should say the pressure a liquid creates when exposed to a vacuum. A liquid needs an atmosphere to exist. A liquid always needs an atmosphere above it in order to remain stable. If you say a liquid needs an atmosphere so badly above it, or wants an atmosphere so badly above it, that if you deny it that atmosphere, it will just create one from itself. If you take water and you put it in a small vacuum chamber and you pump all of the air out, some of the molecules from the water are going to leave that glass of water or that beaker of water, enter the vacuum chamber, create a very thin water atmosphere, gaseous water atmosphere, and that will be the atmosphere that contains the water, or the liquid water. If you put that same glass of water on the surface of the moon, it will try to form an atmosphere, it'll boil, but the volume of space to fill up is way too large, and so it will just evaporate completely. Well, some of it will freeze and half of it will boil. If you put a glass of water on the moon, on the surface of the moon, basically it boils and freezes at the same time. Isn't that lovely? For the record, don't go to the moon without a spacesuit, because you are basically a glass of water in this context. Not in all contexts, but in some contexts. Okay, so again, the question is, what is keeping the fluid in the pipe? What is keeping fluid in the column? And the answer, again, is atmospheric pressure. And I will mention what kind of fluid we tend to use for these. Well, we don't tend to actually use liquid barometers that much anymore, but if you were to construct one, you don't usually use water, and I'll discuss why in a bit. I would traditionally use mercury, so I would have gamma Hg for gamma mercury. And if I want to find the pressure, or if I want to look at this, let me work through the equations of the equations of depth and pressure that we saw in the previous lecture. So if we remember, the difference in pressure in this fluid column from here to here is going to vary based on the depth of the fluid. So P atmosphere minus P1 is going to be equal to gamma times Z2 minus Z1. Or, since P1 is basically 0, P atmosphere is going to be equal to gamma H. P atmosphere is going to be equal to gamma H. Now, interestingly enough, this has certain implications. So, first of all, this explains why we use something like mercury instead of water. The height of the column is going to be directly proportional to the specific weight of the fluid. So let's see. Let's work through those numbers and see what kind of column of fluid we would need for both mercury and water. And for units again, for units of atmospheric pressure, we usually say we often express pressure. Often express pressure as a height and liquid. I.e., like you sometimes see, e.g., 759 millimeters of mercury. This is saying that the current, if I say that the atmospheric pressure today is 759 millimeters of mercury, what I'm really saying is the current atmospheric pressure around us is sufficient to raise a column of mercury 759 millimeters. If I want to see what that looks like in pascals or something, well, I would have to work with the density of mercury. 759 millimeters Hg times 759 millimeters over 1,000 millimeters per meter, or sorry, I should say, that's not working right. Let me just actually use a multiplication factor. I should say 1 meter over 1,000 millimeters. That makes me feel better. Times 133 kilonewtons per cubic meter, which is approximately the specific weight of mercury, and I will get a pressure of 101 kilopascals. So that's approximately atmospheric pressure. Now, again, what if I were to use a fluid other than, so what if I were to use, say, water? What if I used water? That might be tempting. I mean, mercury is, sure, it's dense and it's easy to, it's very visible. It's not clear. You'll very easily be able to measure the height of mercury in a tube. But of course, it's toxic and it has all sorts of drawbacks like that. It's hard to acquire. It can be expensive. It's hard to contain. And if you spill it, then you got to call the hazmat crew, right? So maybe, what if I want to use water instead? Well, let's see. So gamma of mercury is going to be 133 kilonewtons per cubic meter, and the gamma of water is going to be 9.81 kilonewtons per cubic meter. Well, so it's going to be the same pressure though. So 101 kilopascals is going to be equal to I'm using the same P atmospheric equals gamma H equation, equals 9.81 times the height H. And if you do this, you find that H has to equal 10,290 millimeters, or approximately 10.3 meters, or approximately 14 times the height. Think about this for a second. This is a tremendously tall instrument. Something that is only 759 millimeters, that's less than a meter. That's less than 3 feet long. I can easily just fit that on a tabletop. That's something, or on top of a desk. That's something that's an instrument that is very human scale. But something like 10.3 meters, that is 3 stories tall. This is going to be, I'm going to need to sort of build a building around my my water barometer, aren't I? It's not going to be great. And plus, another problem, I'm going to have to be constantly refilling it because water has a tendency to evaporate in a normal atmospheric environment. This does also have another implication, though. In that, since barometers are based upon the concept of atmospheric pressure raising a fluid a certain depth or to a certain height, interestingly enough, this also puts a limit on how high you can pump water with a how high you can pump water vertically, at least using a siphon. So, for example, say I have a mine. Say there's a mine, and deep underground, there's a mine down here, and every mine that has ever been built has had water at the bottom of it. This is kind of inevitable. And so every mine is going to need some way of draining or removing water. And so in modern mines, this is done, in ancient times, this was done through, making a mine on the side of a mountain or something like that, where you could just have water flow out gradually, flow out naturally via gravity. In modern times, we can dig mines pretty much wherever we want. Well, a mine engineer is going to yell at me for saying that, but it's much easier, at least, because we can pump water. We have machines that can pump water, and in fact, the drive to to empty mines and pump water was one of the catalysts for the Industrial Revolution, the invention of the steam engine, and you can read all about that history. But anyway, the point being that let's say I want to pump water from a mine. How am I actually going to do that? Let's say I have my pump here, and it's going to pour water out here, and I have a pipe. Well, I want to put my pipe at the bottom of the mine. That would make sense. And I'm going to pump, this is going to be a qualitative example a little bit, but I just have a long hose or pipe or something going to the bottom. When I pump water here, what's happening really is that the atmosphere down here is pushing against it. And so when I pull water with the pump, the pump is not magic. It can only affect things that are right next to it. This pump here can only affect the bit of fluid in the pipe right here. And so it moves this bit of fluid from here to over here. And when it does that, that would tend to create a vacuum if there weren't other water to take the place of the water that it just moved. And so this is sort of an extended version of the barometer. It's a barometer that we're continually moving water through, essentially. And so what's happening is there is water at the bottom of the mine, and maybe there's a pool of water down here. Maybe at the lowest point in your mine, you have a pool of water that develops, and you just pump water up here. Now, again, what's forcing the water up to go up what's forcing the water in this arrangement to go up the pipe is not actually the pump. What's forcing it is atmospheric pressure. There's P atmospheric pushing down on the pool of water here, and as to prevent a vacuum from forming inside the pump. Most mine pumps and most any kind of pump that needs to move water at this or up a height, they're not arranged this way. How do they actually tend to be arranged? Anyone know? They tend to be at the bottom. Yes, they tend to be at the bottom. And the reason is that that atmospheric pressure can only push a column of water so high. In fact, it can only push water to a height of 10.3 meters. This type of system has a max height is approximately 10 meters. If you make this any longer, you're going to start drawing vacuum, and suddenly you'll have in your system you'll just be pulling out a bunch of water vapor, which pumps tend not to like it when you draw vacuum. It tends to damage the pumps. They tend to make horrible, god-awful sounds, and you know something is wrong immediately. So what they do instead is they actually arrange it so the pump is at the bottom of the mine. Instead, you put your pump at the bottom of the mine. Probably just right. You'll probably use a submersible pump or something like that. Either right in that pond at the bottom, or adjacent to it, etc. And the pump is not limited to atmospheric pressure. It can pump up to the limits of design and materials. So it can pressure this thing to 10 atmospheres or whatever it's required, or 100 atmospheres or whatever it's required to pump the water out of the mine. And this is how you can have very deep mines, say things like, there's some, what is the deepest mine? There are some mines that go even a couple miles deep in certain rare cases. And You may need to use, I don't know if one pump is capable of doing that, probably, but if not, you could even use like more exotic things like staged pumps, like one lower pool pumping into a higher pool, pumping into a higher pool, etc. But again, this system is pulling water. This system is pushing water. When you're relying on atmospheric pressure, you can only pull so far. The same thing would work if you use a siphon. If you were to try to pull water using a siphon, which we'll discuss later on, well, in another lecture. Okay, so let's talk about another means of measuring pressure, and that's the manometer. A manometer is not typically used, or is not really useful for measuring atmospheric pressure, but it is used for measuring. It is useful for measuring pressure in closed containers. So let me just label this mine pumps. Okay, so let me check, make sure we're good here, and yes, we are. Okay. Oh, that's not right. Okay. Sorry, having some technical difficulties here. Okay. Okay, actually. And there we go. Okay, much better. All right, so let's talk about manometers. Let's talk about manometers. So a manometer is a device that measures pressure in vertical tubes. Is a device that measures pressure via a vertical tube. And you can have both closed tube and open tube manometers. If you're using an open tube, it would be measuring relative to atmospheric pressure, so a gauge pressure. If you're using a closed tube manometer, it would be measuring relative to the gauge pressure, atmospheric pressure. So again, open tube would be measuring relative to atmospheric. A closed tube would be measuring absolute pressure. But a specific application of this, a piezometer, is going to have a vertical tube at one end, and it's going to be attached to a container. Our piezometer is going to be a vertical tube, open at one end, attached to a container. A container. Typically a pressure vessel, like a boiler or something like that. So say you have a vessel or a container here that's at a certain pressure, and you have a vertical tube like this here, and there's going to be a free surface. The fluid is going to be, you're going to have the same fluid inside the tube, your measuring device, as you do inside the pressure vessel that you're measuring. So if you're using this for a boiler or something, it might actually work. And this fluid is going to have a certain gamma, and there's going to be a certain pressure A. So this is not for measuring atmospheric pressure. This is just for measuring pressure in a closed container. And this will again raise up the pressure, this will again raise the fluid to a certain elevation h, to a certain height h. And I'm going to call this one maybe point 1. So since we're going to use gauge pressure here, so I'm going to say PA minus P1 which is 0 because gauge. And this is going to be equal to gamma times ZA minus Z1. And we'll get PA equals gamma H. Again, this being a gauge pressure. This is a gauge pressure. Now there's going to be some big disadvantages to this though. Nowadays we tend to use actual more digital systems, but if we're talking about more physical systems, we're talking about more physical, even though we don't tend to use these devices much anymore in industry, we tend to use more digital controls and things. But we're discussing them in class today because they're very useful to illustrate basic properties of fluid mechanics. The disadvantages of them are, first, they're only good for small pressures, else tube is very long. Two, let's see, pressure must be greater than atmospheric. And three, liquids only. Trying to squeeze that in there. And the reason the pressure has to be greater than atmospheric is that this thing is fighting atmospheric pressure. And if this is, say, a boiler, if the pressure in, say, the boiler's on right now or something, if the pressure in your boiler or whatever this is drops below atmospheric pressure, well, suddenly instead of your boiler forcing water into the atmosphere is going to be forcing air into your boiler, which, depending on your system, which is probably not something you want. And so these things are only good for they're for a very narrow range of pressures. They need to be small enough. The pressures need to be small enough that you can actually have you don't want a 10-meter high column or something like that. So they have to be 2 atmospheres, 3 atmospheres, 4 atmospheres, something like that. But they also have to be great enough that they're greater than atmospheric pressure. So they're not so great. And also they have to be liquid and not gas. Have to be liquid and not gas because this won't work for a gas. And also they have to be this fluid has to be the same thing as the fluid that's in your container. So if you have a container full of water, that's not a problem. If you have a container full of hot hydrochloric acid, that might be a problem because there are many kind of containers or kind of substances that you don't want exposed to the atmosphere, either for safety or what if you're doing. Now there may be one case that those pressures might actually work. Might be something like, I don't know, like food processing. You're probably not dealing. You may be dealing with things that are pressurized, but they're not pressurized to, really insane pressures and things like that. But a lot of times you don't want your food product exposed to the atmosphere. So anyway, it depends. Sometimes it can be useful, sometimes not. So anyway, but it is useful for illustrating basic concepts of fluid mechanics. So let's talk about the Utube manometer. And this has nothing to do with the Utube website. This is a U-tube, not W-O-U-T-U-B-E. Utube manometer. All right, so this is useful for measuring the pressure. This actually is useful for measuring the pressure of a gas, not just a liquid. And we're going to use a U-shaped tube in order to do so. So we're going to have this is very useful for measuring the pressure of a gas, especially. As long as whatever gas you're using isn't soluble in whatever working fluid that you're using in the manometer. So you need to make sure that you select a fluid that will be, the gas will not readily dissolve in, otherwise you may have some issues. So I'm going to kind of draw this a bit exaggerated here. I'm going to draw this stretched out and longer than it really is. It's actually more of a U shape. But so if you were to see this in real life, it would look something more like this, like an actual U-shaped tube. But I'm stretching it out a bit so I can fit more fit some notation inside there. So inside, what's going to be driving this is a gas, a gamma, or a pressure for a gas. So this will be both gamma gas and P gas. We'll have a pressure here and a certain gamma. And I'm going to label a few points. Now, let me label a few points. I'm going to label point, oh, and also let me show the fluid first before I label my points. I'm going to have a fluid in here. Now I'm going to assume that the gas is at a a higher pressure than atmospheric. And I know this because as I've drawn it, the fluid column over here is higher than the fluid column over here. So basically we're having two different gases that are fighting each other. Here I'm going to have the gas in the pressure vessel fighting against atmospheric pressure. If they're exactly equal, the two columns of fluid will be at the same height. If atmospheric pressure is stronger, this one will be higher than this one. If the gas pressure is stronger, then this one will be higher than this one. It's sort of a tug of war. We're putting the gases against each other and measuring them directly. So what's really nifty about this is it's a balanced system. So previously we were just measuring the raw height that a gas is capable of pushing. But here we're going to put two gases against each other and then measure which one is stronger, essentially. So something like a barometer can actually measure absolute pressure for your atmospheric pressure, but a Utube manometer is literally physically a gauge pressure device. It is not capable of measuring atmospheric pressure. It is always going to be measuring pressure relative to the atmosphere. So let me label a few points now. Well, I'm going to have point 1, which will be at the same height as the pressure vessel. Point 2, which will be down at the first surface or the lower surface of the fluid. I'm going to have point 3, which will be down at the bottom of the U-tube. Point 4, which will be at the same elevation as point 2, and point 5, which will be at the upper elevation of the upper surface of the fluid, or the right surface of the fluid. And let me label a few points. So, let me label a few heights now, I should say. I'm going to measure all heights relative to 3, just because we always need to give a reference line. And I'm going to define point 3 as what I consider to be 0 elevation. So I'm going to have H2 and H1. Then, let's see. Although for this here, I could call this H4 and 5, but won't really need that for my derivation, so I'm just going to call this one H3. H1 is going to be the difference from 1 to 2, H2 will be from 2 to 3, and H3 will be from 4 to 5. So make sure we have that, and etc. And my actual Z, though, is going to be measured from here downward. So I guess there's a little mistake in there. I'm not measuring my elevation from here. I'm actually kind of measuring from the upper point. Z is going to be from here downward, but I don't need a separate thing for 3 because everything is defined relative to one another. And I am going to apply the hydrostatic pressure equation. Which between points, so we don't confuse 1 and 2 here, what I'm going to do is I'm going to give my generic form of the equation in terms of like A and B. So the generic form of the equation would be something like PA equals PB plus gamma times PA, or times ZA minus ZB. So PB plus gamma times ZA minus ZB. And the way I'm going to work with this, or the way I'm going to think through this, is to recall the following rule. So recall that when you go down, when we go down, pressure increases, and when it went up, decreases. So I'm going to use that to sort of keep my bearings as I'm working through these equations. And we need one more component, and that's going to be, I'm going to call gamma HG, or sorry, gamma GF, which will be the gamma of the gauge fluid. GF stands for gauge fluid. All right, questions on that? Hopefully fairly straightforward. Now I'm just going to work through a series of pressures to kind of tease out the relationship here. Okay, and also it is important to notice that the pressure here, the gas at this, the gas in the container here at point, let me call this point A. The gas at point A is pushing directly on the gauge fluid. Okay, so I'm going to work through. Basically, what I'm going to do is I'm going to start at point 1, find the pressure there. Point 2, the pressure there. 3 there. 4 there. 5 there. I'm just going to work through it in a series of steps. So now, first I'm going to calculate the pressure at point 1 based on PA. 1, calculate pressure at point 1 based on the pressure at A, or P gas. All right, so I'm going to say that P1, well, P1 equals P gas plus gamma times Z2, or times Z1 minus ZA. So basically I'm going from here to here. And however, there is no difference in elevation, so this term is 0. Therefore, this leads inexorably to that P1 is equal to P gas. No surprise there. Now the next one does get a little more tricky. And the next one is a bit of a head scratcher, but it makes sense if you think about it. Calculate pressure at point 2, or I should just say, you know what, at 2 based on P1. Well, I can work through the equation, and we'll see that P2 equals P1 plus gamma gas times Z2 minus Z1. So in other words, if I go from here to here, the pressure will increase a tiny bit due to the increased depth of fluid. However, let us consider this. Let's consider this. This difference in height here. It's important to consider that the difference in height here, what is that relative to? That difference in height is actually relative to this is a gas, so it's relative to, well, if it was an atmospheric gas, we'd be measuring that height relative to the entire column of the atmosphere. And since this gas is higher than atmospheric pressure, that relative height would be even greater. So in other words, that little difference in height for a gas is going to be negligible. In other words, the difference in pressure between here and here, because the density of a gas is so small that we can really neglect it. That is essentially 0. With liquids, because there's no mile-high column of liquid, it's not really that significant. But when you have a mile of atmosphere, the difference in gas pressure between here and here is negligible, so we don't even need to really consider it. So I am going to neglect that and just say that this term drops away and is insignificant as well. Or another way I can conceptualize this is that compared to the fluids, the gamma of the gas is approximately 0. So this time this term drops away. So now I have P2 is equal to P1 is equal to P gas here. Is equal to P gas. Now, let's see. My next step, I'm going to calculate the pressure at 3 based on the pressure at 1. Or the pressure at 2, sorry. Again, I'm just kind of working through it. Pressure at, and that should probably say on 1, at 3 based on 2. And again, we'll do the same kind of thing, except this time it won't cancel out. And I will get that P3 is equal to P2 plus gamma gauge fluid. This is where the gauge fluid actually shows up. Gamma gauge fluid times Z3 minus Z2. And this leads us to, inevitably, that P3 equals PA plus gamma GF times H2. P3 equals PA plus gamma GF times H2. And so, again, we're just saying that the pressure will increase from 2 to 3 based off of the idea that the fluid is going into a lower elevation. The gamma GF represents the specific weight of the gauge fluid, yes. GF in this context does not stand for girlfriend, it stands for gauge fluid. There's a joke there, but I'm too uncaffeinated to make it properly. Okay, moving on. I have 2 more steps I want to work through. And then I'll sort of synthesize all this together into a final form. For calculate P4 given P3 and P4 equals P3 plus gamma GF times Z4 minus C3. However, this whole thing here, Z4 minus C3, that's what I defined as H2. That's H2 here. And P4 then, let's see. P4 is going to be like this. Now, what happens if I plug in, so again, I'm looking at the pressure at point 4 here. Now, I have this expression for P4, and it includes P3. What I want to do now is I'm going to plug in the previous expression I derived for P3. So, I'm going to I'm going to plug that in here. Okay, so let's look at this now. Let me plug in the previous expression for P3. This is going to be P gas plus gamma GF times H2 plus, again, this here, gamma GF times H2. Gamma GF times H2. Oh, actually, sorry, this is not gamma H2. This isn't H2. This is actually negative H2. Sorry about that. There should be a negative sign there because we're increasing in height. So gamma GF times negative H2 and there would be a closed bracket there because I'm substituting in. And we can see then that these two terms are going to cancel out. And so this will lead us then to P4 is equal to P gas. And really this doesn't surprise us. These two are at the same elevation. If point 2 is at P gas, then P4 is actually at P gas as well. So this also illustrates that if we're working through systems like this, we don't actually need to go to point 3. We can, as long as they're at the same elevation and the same fluid in between, we can jump directly from point 2 to point 4. And then finally, let's work through point 5. Let's look at point 5. Let me put a box around that. That's what I've been doing. Nice bright red box. Here. And let's work through one final step, which will be to find the pressure at 5, which is what I was really going for. Sort of. Calculate P5 given P4. Now, P5 is going to be equal to P4 plus gamma GF. So the pressure should decrease again because we're going up in the fluid. Z5 minus Z4. And I'm going to then have P5 is equal to P4 plus gamma GF times negative H3. Now, let's see. There is one thing that I can make 0, though, and that is actually P5. P5 is directly exposed to the atmosphere. Oh, that's not right. Okay. P5 is directly exposed to the atmosphere. It's going to be, okay, I'm just having a little technical difficulties today. I don't know why. Okay, having trouble with my slides this morning. P5 is directly exposed to the atmosphere. Therefore, it is 0 because this is gauge. So, therefore, I can then determine that P gas is simply going to be equal, if I do some substitution, etc. Oh, and sorry, this should say, since P4 is equal to P gas, I can actually say this is equal to P gas. And so then P gas is simply going to be equal to gamma GF times H3. And that's really the derivation I was after. The gauge pressure of the gas, then, is simply going to be, if we look at this, if we go back to this, the gauge pressure of the gas here is going to simply be equal to the difference in height between the fluid columns times the gamma of whatever gauge fluid you're using. And now you have something that's actually useful. So again, this is measuring pressure relative to the atmosphere. You don't need a really high tube. You don't need, you can actually measure the pressure of a gas. And the gas itself doesn't actually have to be exposed to the atmosphere, which is obviously beneficial. So that's the basic idea of manometers, barometers, and Utube manometers, and I think that will do it for today. So that's just what I wanted. I just wanted to introduce some methods of measuring pressure, and that'll do it for today. So if you have any questions, feel free to see me during office hours. This video will be posted shortly, and as always, thank you.